Right now, there are two completely different realities in the tech world. In reality A, you have the AI hype cycle. That's full of flashy dashboards, overnight breakthroughs, and of course, vendors promising you a magic button for your organization or solutions that will solve the world's problems tomorrow. Then you have reality B. Reality B is where you and most people live. This is the reality of, say, securing a sovereign wealth fund, managing critical infrastructure, or tracking global health trends. In reality B, the data is messy, the physical context, our environment matters, and the stakes are incredibly high. And the problem is that the tools being pitched in reality A simply do not survive contact with reality B. You can't build your organization's future on a generic algorithm that lacks the deep scientific context of the real world. We won't build an AI model that simply solves security, global warming, hunger, or disease. But what we can build are sovereign, precision-engineered systems that give the experts who are fighting those battles the exact intelligence they need to win. I spent the last 25 years navigating this tension between what technology promises and the reality of our very dynamic, changing world. I spent 14 years as a researcher at Penn State, diving into the why. Why should we do this? Why should we build these systems? Before that, 4 years in the tech industry, and over 7 years more recently as a consultant, building the how. How are we going to build this? What I've seen is that the real innovation gap isn't just about the code. It's about the bridge between scientific rigor and production-grade execution. Today, let's talk about a different direction. We're going to look at geospatial foundation models, not just as another tool, but a new way for us to perceive the Earth. We'll talk about why sovereign AI is becoming the gold standard for organizations that value data integrity. And I'm going to show you how an interdisciplinary workflow doesn't replace your 20-person team, but it acts as a force multiplier, unlocking them and accelerating the entire department. So, enough about what the tech might do someday. If you're ready to see how we build private, production-grade Earth intelligence right now, let's get to work. Let's start with the what. What has actually changed in the last few years? For a long time, geospatial analysis was brittle. If you wanted to find, say, flooded houses, you would perform time-consuming local analysis, or train a specific flood model, or create a custom geospatial index of data. If the sensor or the resolution changed, the model broke. And it would likely only be applicable in a small area or a narrow time range. If you wanted to do something on a broader scale, it would probably be more general or coarser. But now we've moved into an era of the geospatial foundation model. We're talking about massive models, such as one is Prithvi and Clay is another. These aren't just apps. They are neural networks, deep learning models, pre-trained on millions of satellite images and atmospheric readings. And they don't just see pixels. They understand the patterns of the Earth. Once the models know the standard Earth ecosystem patterns, they can help us quickly fine-tune them for specific tasks. We can uncover knowledge or detect anomalies, things that don't fit those normal patterns. And these are sometimes the most critical. When I look at these models, what gets me excited isn't just the accuracy, it's the speed. We are seeing a massive increase in speed in turning these pixels or sensor readings into insights compared to, for example, old school, whether it be unsupervised or even supervised methods. Think about that. If you're a consultant for a bank, a utility company, an energy company, and you can simulate 1,000 climate risk scenarios in the time it used to take to run just one, your entire relationship with risk changes. You move from being reactive to being predictive, making decisions based on accurate probabilities rather than hunches. But the catch is that these models are only as good as the data you feed them. And for most of you, your most valuable data is proprietary and sensitive. It's a matter of national security or perhaps corporate survival. This aspect leads us to the biggest recent shift, the move towards sovereign AI. There's a reason I still keep my hands on the keyboard to build, to code, and configure these systems. Talking about AI theoretically is one thing, but you really need to see what these architectures can do when you put them to work in real-world applications. I still run many of my initial prototypes on the dual GPU setup I have right here. Obviously, when I scale to continental projects like the World Health Organization simulation, I will migrate to larger GPU clusters. But the underlying mechanics are the same. Whether you are a leading environmental agency, a major energy company, a sovereign wealth fund, a national bank, or perhaps a major insurer, or anything in the middle, sovereign AI comes down to one absolute requirement: control. You simply cannot afford to pipe your proprietary data intelligence into a public black box. Because of this and other reasons, I've been saying this a lot lately. We need to move from being AI users to AI creators. To do that effectively, we use open models, such as Clay and Prithvi for Earth observation, or the open LLMs like Llama, the Llama family of models, for text content. And we securely pull them behind the firewall. A general public model is a great starting point, but it doesn't know your business. When we build sovereignty, we fine-tune that model on your data, giving it that local context it needs to understand your specific geography and operations. So, how do we actually get this done? Usually, a CIO thinks they need a data science team, a data engineer team, testers, maybe a DevOps crew. But the problem I've seen over my 25 years is that these groups, they speak different languages. Things get lost in translation. Moreover, the CIO or top managers, they're typically left to interpret or simply guess what the domain experts over there actually want. And this gap is my sweet spot. Because of my time as a researcher in the interdisciplinary unit, I understand the science, whether it's national intelligence, epidemiology, machine learning, or geospatial statistics. And because I've spent more than a decade in top-tier tech and consulting, I also know how to turn this into production-grade code that simply makes the application work. When you have a bridge between these worlds, you don't need a 20 to 50 person team to start. You need a unified pipeline. You need someone who can look at the domain use case, the application architecture, storage practices, raw SQL queries, train and optimize a machine learning model, and then wrap all of that into a visualization that an executive can actually use. Now, at this point, you aren't managing a crowd, you're managing the result. And a quick side note for anyone watching this who's early in their career. I cannot emphasize enough how important it is to build interdisciplinary skills and knowledge. Don't let yourself get boxed into, you're just the database person, or you're just the UI person, or you're the GIS person. Learn the domain science, learn the infrastructure, and learn how to talk to executives. Why? Because the tools and the coding syntax will constantly change. But the ability to translate a complex scientific problem into a working production-grade system, this never goes out of style. With AI getting smarter and knowing more these days, the future really belongs to people who can connect the dots and link different areas of expertise. Let's look at a concrete example. I'm building an AI-based disease prediction system for the World Health Organization. It focuses on meningitis, malaria, and a couple of other initial diseases across the WHO Afro region. In a traditional setup, this data is messy and disconnected. But by applying a geospatial foundation model framework, we don't just look at case numbers in a vacuum. We feed the model variables such as temperature, precipitation, land use changes, which the foundation model already understands patterns at a global scale. In addition, Earth observation data and even population data, they have gaps from the time from satellite passes, clouds, dust. In the case of population, from the lack of historical data, time and computation to produce accurate weekly results. The foundation model can help fill those gaps. The foundation model serves to fuse these disconnected datasets into a cohesive unit. By acting as the connection among data engineering, machine learning models, geospatial foundation models, and of course the UI and the user, my goal is to remove the friction that usually stalls these projects. Instead of spending months handling data back and forth between isolated departments, we can move seamlessly from raw data and SQL to a working simulation that predicts an outbreak before it happens. And that speed is what turns Earth intelligence into a tool that actually saves lives. But here is the reality of operating at that level. Speed means nothing if the people in charge don't trust the system. When you're predicting a continental disease outbreak, you can't just walk into a boardroom or a regulatory agency and say, oh, the AI told us to do it. You need an audit trail. You need explainability. If the model makes a mistake, or if it uncovers a massive unexpected risk, you have to be able to pull back the curtain and explain exactly why the system made that correlation. A comprehensive explainability is where the interdisciplinary workflow becomes your biggest asset. When you rely on a fragmented team, where the developers don't understand the science, and the scientists don't understand code, you inevitably end up with a black box. But when you bridge that gap, when we build the architecture with a deep understanding of the underlying epidemiology or the AI, you don't just output a prediction. You build a system that can explain its reasoning in the language of the domain experts. Whether we are designing AI datathons for a major bank, or integrating highly sensitive data for a progressive government environmental agency, the mandate is the same. The intelligence must be defensible. When you bridge the gap between raw code and the data and the physical science, you stop selling magic to your stakeholders. You hand them a scientifically sound, transparent architecture they can actually trust. Once the system is something both executives and regulators really trust, then we can stop looking at old data and we can start actively running simulations to see what will happen next. We are moving away from static 2D maps and into the era of predictive Earth intelligence. And to understand what that actually means, we have to look at geospatial foundation models like Prithvi. Prithvi was built collaboratively by NASA and IBM. In late 2024, catastrophic floods hit Valencia, Spain. Traditional satellite mapping failed because heavy storm clouds literally block the sensors from looking down. But Prithvi isn't just a sensor. It's a model trained to understand Earth's physical layers. By combining standard optical or visual imagery with radar that cuts through the clouds, Prithvi was able to map the exact boundaries of the floodwaters beneath the storm, significantly outperforming older methods. But mapping the Earth is only half the battle. You have to connect that intelligence to your physical assets. Look at the EU's Nature Demo project. They use this exact type of foundation model data to support critical infrastructure directly. When you combine a foundation model's predictions with a digital replica of your own assets, then you enter into the era of agentic AI GIS. Instead of a CIO or a city planner clicking through map layers, guessing what's next, trying to connect the dots, You can ask the system a direct question. Based on the AI's flood prediction, which specific railway embankments or energy substations will fail under the physical stress of the water? The foundation model maps Earth's reality. The digital twin calculates the physical stress of your infrastructure. And the AI agent, it reasons through the problem to pinpoint the exact intervention points before anything breaks. This scenario means it's time for a major upgrade, ditching the overwhelming, disconnected data and focusing on pulling out the real knowledge we need to move forward. If you've stuck with me this long, you're clearly thinking about how to move your organization into this next era. My advice, don't wait for that pre-packaged solution from the big vendor. They build those solutions for the average user or the common use case, and you aren't average. If you're building something that hasn't been built before, something that requires a sovereign, secure, and scientifically grounded approach, that's where the value is. Believe me, with out-of-the-box solutions, you can solve this amount of challenges. But with custom solutions built with and for domain experts, you can solve this amount of challenges. And if you're in business, implementing that out-of-the-box solution will be the same thing that your competitors are doing, so you won't gain that competitive edge. If your team is trying to solve problems that don't yet have that prepackaged answer, then let's connect. Leave me a comment below. What's the biggest integration hurdle you're facing right now? Is it data, hardware, finding people who speak both the languages? When you discuss topics like these with your peers, are they looking at you with blank stares? Hit the subscribe button for more deep dives into technical stacks, from deep learning to geospatial workflows to optimization and visualization. The next video will expand upon the bridge approach by showcasing how computer perception extracts meaningful order from the noise of urban environments where most of us live. I will demonstrate how sophisticated models are discovering hidden signals within cities. These applications include quantifying the stresses of city life by analyzing decades of photos and satellite imagery, and even identifying the early signs of gentrification. The core focus is on revealing urban structures that are imperceptible to the human eye, especially at scale. If you want to see how we can apply this interdisciplinary approach to your mission, reach out to me. Let's build the future of Earth intelligence together. I'm Scott Kozanowski, and thanks for watching, and I'll see you in the next one.